Hello, today's topic is internal forces in beams, and this is part 2. Example 3. In this section, I will show you how to draw the internal force diagrams for simple beams, and how to do it quickly and efficiently without writing equations. Some professors require writing equations to draw internal force diagrams, so you need to make sure whether those equations are necessary for you, or if you just need to draw the diagrams and that's it. Without writing equations, the diagrams are drawn much faster. Let's move on to the next example. In this example, we have a continuous load resting on a support and extending further, a moment of 15 and a concentrated force of 10 kN. So just like before, I am not introducing horizontal forces or forces at an angle in these examples to draw the normal force diagram, because the normal force diagram for simple beams is trivial. Therefore, the horizontal component of the reaction from the fixed support D is equal to 0. Here we have reaction VB and reaction VD. Now we will take the moment sums at any point. From this, we will calculate one reaction, then the sum of projections on the y-axis, and we will get the second reaction. So we will write the moment sum at point D, marking the resultant for the continuous load as well. We don't need to break down this resultant to calculate the reactions into the part that is on the left side of the support and the part that is on the right side of the support. We can simply take the resultant of the whole, and this resultant will equal 10 times 6, which is 60 and is in the middle of the entire load. So we need to be well oriented about exactly where it is. If the load is at 6 meters, then it is 3 from the left side and 3 from the right, so we are 1 meter from the support with this resultant. So 10 times 8 minus, I wrote here 10 times 6, which means 60 times 4 and 1 more, which means times 5 minus moment 15 plus VB times 4 equals 0. From this, VB is equal to 58.75 kilonewtons. The sum of projections on the y-axis equals 0. 10 plus 58.75 minus 60 plus VD equals 0. From this, VD should be equals minus 8.75 comma, so as before I put a plus and change the direction of the reaction VD to the opposite. We have calculated the reactions, now we can start drawing the diagrams. We look at the load on the beam from the left side. At first, there is a jump of the value of the shear force, which is applied here, 10 upwards. Now, we need to divide this continuous load, because here when we go down, there will be a jump of the value of the reaction VB. So we need to break it down into what is on the left side of the support and what is on the right side of the support. We will make two resultants. So here we have 4 times 10, which is 40, and on the other side we have 2 times 10, which is 20. So starting from the value of 10, now going down linearly by 40, which brings us to a value of minus 30 at this support. Here it is linear, so here it is 30. Next, we have a jump of the reaction VB value, which is 58.75, and the jump goes upward. That is towards the positive. And we are at minus 30, so to 28.75. We have a jump, 28.75. Then we have a linear drop of 20, that is to 8.75, and that is a positive value. Then here on this part of the beam there is no shear force, so a constant value. And the reaction VB is how much? 8.75 comma, that's correct, so this reaction brings this graph down to 0. So here, as we reach the end to the value of this reaction, it means that it is good, so we have certainty. Now with a continuous load here, we have a sign change. So at this point on the moment diagram, we will have an extreme value. Okay, I will calculate this using the areas of figures from the shear force graph. This example is simple. I mean the values and lengths of the beam, but let's calculate for the general case. Here is some x that we would like to calculate. This value x is always the value of that shear force, which is on the left side. That is 10 times the length of the beam, so we are interested in 4 here. Divided by that plus that is by 40 and that is 1, which was easy to deduce, but this will work for every case. And the area of this triangle is 10 times 1 times 1/2, that is 5. The area of this triangle is, since here it is 1, then it is 3 times 30 times 1/2, that is 90/2, so 45. The area of this trapezoid is a plus b times h/2, so that is 37.5. And the area of the last rectangle is 8.75 times 2, that is 17.5. And drawing the moment diagram, we remember that here we have 15, so do we have some moment at the end of the beam applied? No, it should be 0. Do we have some moment here? No, we have to go down to 0. So, from this 0 first, by the value of 5, that is of this area, towards the positive, that is down, so here is 5, and we move parabolically because the shear force graph was linear. This is a parabola. This is the maximum value. This is the maximum value because from here we move by 45, but already towards the negative we go. So from this 5 by 45 towards the negative, that is to a value of minus 40. So to the value of 40, and it looks like this. Now from this 40, that is here is positive, here is negative. From this 40 towards the positive, that is again down. Again a parabola by the value of 37.5, that is to 2.5. Here is the jump. I thought I missed it. So to how much? To 2.5 parabola. Next, the moment is negative. So we have from negative 2.5 a jump of minus 15, that is to minus 17.5. Here the value is 17.5, and as you can see, it will be okay. From this 7.5, which is negative, we have to move towards the positive by 17.5 precisely. There was a constant value on the shear force graph, so the moment diagram changes linearly. Of course, here the scale is not properly maintained because here is 7.5, and here almost equally is 40, but you have to forgive me. And so, as you can see, it can be done quickly. We can say here with a high degree of certainty that this is good, because we came down to 0, so it would be hard to make a mistake to the extent that these numbers would match like this, that going from the left side we always end up at 0, which is as it should be, because we know that. That's it. Thank you for your attention. I hope I helped. If you have any questions or comments, feel free to ask and leave comments under the video. I also recommend the other productions, encourage you to visit our website, and like our social media. And of course to subscribe to this channel so you can stay updated with new videos from EduPanda. In the meantime, thank you very much. Best regards. Goodbye.